Every time you call session, save in your Java app, something happens behind the scenes that most developers never think about. Hibernate is doing a lot more than just running SQL. It's managing object identity, tracking dirty state, scheduling flushes, and coordinating with a first-level cache all invisibly. In this video, we'll pull back the curtain on exactly how Hibernate works under the hood, from the moment an object enters the session to when a transaction commits. So let's start with the core question: what actually is Hibernate? At the surface level, it looks like a convenience wrapper. You write Java objects and Hibernate writes SQL for you, but that framing misses everything interesting. Hibernate is a stateful object graph manager. It doesn't just translate objects to tables, it maintains a live model of everything you've touched inside a unit of work. That model is the session, and understanding the session is the key to understanding everything else. When you open a session, Hibernate creates an isolated workspace. Every entity you load or save becomes part of that workspace's identity map. Hibernate holds a reference to each object and watches it for changes. The first level cache is where the magic starts. When you call session, get with an ID Hibernate has already loaded. It doesn't hit the database at all. It returns the exact same Java object from memory. That's not a copy, it's literally the same reference. This is how Hibernate guarantees object identity within a session. The same row always returns the same Java instance. The cache is not a performance optimization bolted on, it's a structural contract. It means you can load the same entity 100 times and only pay for one database round trip. It also means mutations are tracked automatically. If you change a field on that object, Hibernate knows, because it's still watching the same reference it gave you earlier. Now, how does Hibernate know what changed? This is dirty checking. When a transaction opens, Hibernate takes a snapshot of every entity in the session, a deep copy of the field values at the moment of load. Just before flushing to the database, it compares the current state of each entity against that original snapshot. Any field that differs from its snapshot value is dirty. Hibernate then generates the minimum SQL required to bring the database in sync. One update per dirty entity, only the columns that actually changed. You never write a single update statement. The trade-off: Hibernate must hold 2 copies of every loaded object's state in memory and must walk the entire entity graph on each flush. For sessions with thousands of entities, this can become a bottleneck, and it's the most common cause of unexpected memory pressure in Hibernate applications. Flushing is the process of synchronizing the in-memory session state with the database. By default, Hibernate flushes automatically before each query and at transaction commit. This guarantees that a query always sees the freshest state. But it means an innocuous select can trigger a cascade of insert and update statements. The flush mode is configurable. Commit flushes only at transaction end, lower overhead, but queries might see stale data within the same transaction. Manual gives you full control. Hibernate never flushes unless you call session. Flush explicitly. Understanding when Hibernate flushes explains a whole class of puzzling behaviors. Why a read-only query sometimes generates writes, why performance degrades under large sessions, and why the order of operations sometimes matters more than you expect. Now let's talk about entity lifecycle states. An entity can be in one of 4 states: transient, persistent, detached, or removed. Transient means the object exists in Java, but Hibernate has never seen it. No ID, no snapshot, no tracking. The moment you call session, save or session, persist, it becomes persistent. Hibernate assigns it to the identity map, takes a snapshot, and schedules an insert. Detached means the entity was once persistent. It has an ID, but the session that owned it has been closed. Hibernate is no longer watching it. Changes to a detached object are invisible until you call session. Merge, which copies the detached state into a fresh persistent instance. Removed is self-explanatory. You've called session. Delete, and Hibernate will issue delete at flush time. The second level cache sits above individual sessions, shared across the application. While the first level cache lives and dies with the session, the second level cache persists between transactions. You opt entities in by annotating them with cache and choosing a concurrency strategy. Read-only is the simplest and most performant. Hibernate caches entity data after the first load and never invalidates it, perfect for reference data that never changes. Read-write adds lock-based invalidation on writes, slower but safe for mutable data. NO and strict read-write sacrifices strict consistency for speed. Acceptable when stale reads for a brief window are tolerable. The second level cache can eliminate entire categories of database load, but it introduces the hardest to debug consistency problems in a Hibernate application, especially in clustered environments where cache invalidation must cross JVM boundaries. Query cache is a separate, often misunderstood layer on top of the second level cache. It caches not entity data but query result sets, specifically the list of IDs returned by a named or criteria query. When the same query runs again with the same parameters, Hibernate returns the cached ID list and resolves each ID through the second level or first level cache rather than hitting the database. The query cache only makes sense when the same query runs frequently and the underlying data rarely changes. Its invalidation is aggressive. Any write to a table referenced by a cached query invalidates all cached results for that table. In write-heavy applications, the query cache can actually hurt performance by burning CPU on invalidation while providing almost no cache hits. Lazy loading is Hibernate's strategy for not loading data you might not need. Associations one-to-many, many-to-many are lazy by default. When you load an entity, Hibernate creates a proxy object for each lazy association. The proxy looks like the real collection but contains no data. The first time you call size or iterate, Hibernate fires a SQL query to load it. This is the source of the most famous Hibernate performance problem, the n+1 query problem. If you load a list of 100 orders and then iterate their line items, you get 1 query for the orders and 100 queries for the line items, 1 per order. The fix is a join fetch in your query, which tells Hibernate to load the association eagerly for that specific request without changing the global mapping. Understanding this trade-off, lazy by default, fetch eagerly when you know you need it, is the central skill of working productively with Hibernate. Thanks for watching.